This video is about titration, which is a volumetric analysis technique. Titration is a quantitative analysis technique, so that means we're coming up with numbers, trying to find some specific quantities about an unknown. A key tool in titration is something called a burette. A burette is a long skinny tube that has markings on the side of it that can measure volumes, but they don't measure how much volume is in the container, in the burette. Instead, it's designed to measure how much volume came out the bottom. And it comes out the bottom because there's a valve at the bottom. So you'll do a reaction between the titrant, which is the stuff in the burette, and an analyte, which is the stuff that's below the burette in some kind of a container, usually a flask, sometimes a beaker. So you have two different reactants, one in the burette, one in the space below the burette, and you're going to react them kind of slowly and with measurement until a visual cue or an instrumental cue tells you that you're finished with the reaction. And when the reaction reaches completion, we say that you're at the end point, or the titration. And then once you gather the information, stoichiometry, the volume that came out of the burette, and the concentration of one of the solutions allows us to calculate the unknown that we're trying to find. Okay, so here's the general titration process. First of all, start out with a clean burette. Then you want to take a little bit of your titrant, which is the stuff that's going to end up in the burette, and add a small amount, and then you're going to invert it, close the end and flip it upside down, and just give it a good rinse with your titrant. This step is particularly important if cleaning your burette happened just recently and there's some water in there, because you want to make sure that the titrant doesn't get diluted by any drops of water that were hanging around in the burette after cleaning. Then the next thing you're going to do is you're going to fill it up past the top mark, which will be the 0 mark up at the very top. And then you're going to open the valve and let a little bit drain out to fill the tip at the bottom and to let the level of the liquid in the burette drop down below or at the 0 mark. And then close the valve, and then you're ready to make your initial reading. That's the next thing to do. Get your eyeball level to the meniscus, read at the bottom of the meniscus, and most burettes have a marking every 1/10 of a milliliter, so you want to measure to the nearest 100th of a milliliter. Now you have your initial burette reading, and you're ready to prepare your analyte. So the first thing you do is find out how much volume you're supposed to add of your analyte, and get a measuring tool like a pipette. Usually a volumetric pipette is what's being used here, and transfer that amount of your analyte into the flask. Now you're ready to do your titration. So you begin with no titrant in your flask, and then as you add titrant, slowly, you're going to begin to start seeing color begin to change. And when that color is persistent, that color change sticks around for 5 seconds, and you don't want it to be too dark, don't want to overshoot, you want to just barely be able to see that color change. That's your cue that you're done, that you've reached your endpoint. Then you make your final burette reading, and again, you're reading to the nearest 100th of a milliliter, and you want to make sure that your eye is level with the meniscus so you don't get some parallax error. Then you find the volume of the titrant that came out of the bottom of the burette by subtracting the ending volume minus the starting volume reading. And then it's time to find your unknown by doing some stoichiometry calculations. The best way to learn how to do this is by example. So let's do 2 example titrations. So here we have some H2SO4, this is sulfuric acid, in the flask. And we know we have 15.00 milliliters of it, but we don't know its molarity. So our task is to figure out what is the molar concentration of the H2SO4. In the burette, we have 0.147 molar NaOH, and the beginning volume reading is 0.15 milliliters. It's important to know what the chemical reaction is here so we can do stoichiometry. So what's happening here is the H2SO4 in the flask is reacting with the NaOH that's coming from the burette, and that's going to give us water and Na2SO4. This is a double replacement reaction. It's an acid-base neutralization. It's not balanced. We have 2 H's in the H2SO4, So that's going to require 2 OHs, and it's going to make 2 waters, and then that 2 in front of the NaOH also balances Na2SO4. Okay, so let's say we do the titration. This would probably be done with an indicator, an acid-base indicator, something that changes color. In this case, it changes to a pink color when we reach the equivalence point. And at the end point, we have 36.57 milliliters as our final volume. So let's go about figuring out what was the concentration of the H2SO4. Well, first, we can find out the volume of the titrant delivered by taking 36.57 milliliters and subtracting 0.15 milliliters, and that tells us that 36.42 milliliters came out of the burette. So now we're going to do some stoichiometry with that. 36.42 milliliters was the volume. We know that the concentration was 0.147 moles of NaOH for every liter. So now we have millimoles. The liter parts cancel, but the milli doesn't. Our mole ratio is 2 moles of NaOH reacted with 1 mole of H2SO4. So now we have moles of NaOH gone, and what we have left is millimoles of H2SO4. So we do this calculation, we find out that we have 2.68 millimoles of H2SO4. Our task was to find out the concentration, so we'll take the millimoles, 2.68 millimoles, and we'll divide by the milliliters of H2SO4 that we had in the flask originally, 15 milliliters. Now the milli part cancels, and we have moles per liter, which is molarity, and that is 0.178 molar. This is a redox titration. So here's the net ionic equation, and it's balanced for us. There's MnO4 ions in the burette as part of KMnO4, and there's iron 2 ions that are dissolved in acid in the flask. Now clearly that top reaction is missing some stuff. There's no water, there's no H+, but that part has just been stripped out, and we have the mole ratio that we need, which is the ratio between the iron and the MnO4 1-. Okay, so we take an initial reading. It's 1.26 milliliters. We know the concentration of the MnO4 1- is 0.1 molar, and we don't know how many moles of Fe are in this flask. So after we find the equivalence point, now we can find out the volume delivered. So that's 28.71 milliliters minus 1.26 milliliters, and that gives us 27.45 milliliters delivered. So if we take 27.45 milliliters, knowing that the concentration is 0.1000 moles per 1,000 milliliters, and I want to get rid of the milli part this time because I'm not going to divide by a volume later. So milliliters are canceled out. And that was moles of MnO4-. Then my mole ratio comes in here. There's 1 mole MnO4- for every 5 moles of Fe2+ that reacted. So now I'm at moles of Fe2+, and then I can calculate this out, and it comes out to 0.01373 moles of Fe2+. I want to know how much iron that is in mass, so I'll take my 0.01371 moles of iron, and I can just use iron and ignore the missing electrons there because they don't weigh hardly anything. I'm going to multiply by the molar mass of iron, 55.847 grams per mole, and that tells me that 0.7665 grams of iron were in that sample that got originally dissolved in the flask. So 0.7665 grams of iron were in a 2-gram sample of the ore. So if we wanted to know what percent of the ore was iron, it was 38.33% iron by that titration.